So the elements of a set can also be elements of another set, and we refer to these as subsets. So if we have this certain notation, it means that A is a subset of B. And that essentially means that a set B contains set A, or that every element or all elements of A is also in B. I'm expressing it using quantifiers. We have for all x, if x is in A, then x is also in B. Okay, so we can visualize it using a Venn diagram. We can see here that A as a subset of B. So we can see that B contains A, and that every element of A or all elements of A is also in B. Okay, so suppose we have these examples. We have A with elements 3 and 9, and B has elements 5, 9, 1, and 3. So can we consider A as a subset of B? Yes. Yes, we can consider it as a subset. Why? Because every element of A is in B. Okay? A has only elements 3 and 9, and 3 and 9 are also in B. Now, suppose A has elements 3, 3, 3, and 9, and B still has elements 5, 9, 1, 3. Can we consider A as a subset of B? Yes, we can. Because a property of set is that it has no duplicating elements, or it has distinct elements. So we can rewrite this into the form of just 3, 9. And we already know that 3, 9 is in B. So we can say that A is still a subset of B. So suppose A is a set with elements 1, 2, 3, and B has elements 2, 3, and 4. So can we say that A is a subset of B? No, we cannot. Because there are some elements in A that are not in B. So as we can see, A has 1, 2, 3. And only 2 and 3 in A is in B. 1 is not in B. So since there are some elements in A that are not in B, and B does not actually contain A, we can say that A is not a subset of B. Okay, so A is a using this notation, it means again that A is a subset of B, and that B contains A, or every element of A is also in B. Meanwhile, this notation flipped horizontally means that A is a superset of B. Okay, in this case, A is the one that contains B, or all elements of B is in A. So that is the difference of the subset and the superset. Okay, so what about A equals B? What does that mean? Now, if you remember set equality, so we say that two sets are equal if and only if two sets A and B have exactly the same elements. And we can express that using the form of subset. And if and only if A is a subset of B and B is also a subset in A. Essentially, what that means is that all of the elements of A is in B. Meanwhile, B is a subset of A means that all of the elements of B is in A. So if these two are correct or valid, then we can say that two sets are equal. And we can express it using quantifiers and logical equivalence form in the form of biconditionals, that for all x, if x is in A, if and only if x is also in B. Okay, so this is an example of an equal set. So even if these two sets have the same values, right? So 1, 2, 3, 4, and 5. The other one has 5, 4, 3, 2, 1. And even if they have different orders, but since all of the elements of A is in B and all of the elements of B is in A, then we can say that they are equal. Okay, and a subset has also this property. if A is a subset of B, and B is also a subset of C, then we can say that A is a subset of C. So we can visualize it using this Venn diagram. So we have a set A, and A is a subset of B. And for the second term, we said that B is also a subset of C. Okay, so we can see graphically here that A, is also a subset of C. Okay, now note that any set is a subset of itself. So suppose we have a set A 2, 4, 6. So all of the elements of A are elements of A. So A is a subset of itself. So this is kind of like saying 5 is less than or equal to 5. Thus, for any set A is a subset of A or itself. Okay? And meanwhile, we also have the empty set. An empty set is a subset of all sets, including itself. Okay? So recall that all sets are subsets of themselves. Okay? So if empty set is also a set, then taking the subset of an empty set, we also have an empty set as its subset. Okay? Okay, naggamon na. So anyway, we can denote it using this notation. We have the empty set is a subset of A for any set A. So all sets are subsets of the universal set. So we can summarize it in these three useful rules. So A is a subset of A for any set. Okay, so A is a subset of itself, and the empty set is a subset of any set A, of any set. And if A is a subset of B and B is a subset of C, then A is a subset of C. All right, so now moving on, we also have the term called the proper subset. So what are proper subsets? So if A is a subset of B, meaning B is containing A, or that every element of A is in B, but there is a twist. A is not equal to B. Okay, then we can say that A is a proper subset of B. So let's have this example. We have a set B, which has elements 0, 1, 2, 3, 4, and 5. And A has elements 1, 2, and 3. Okay, and from this, we can already see that A is a subset of B, given that all of the elements of A is also in B, right? But we can say also that A is not equal to B, because there are some elements in B like 0, 4, and 5 that are not in A. So we can say that A is not equal to B, and but A is a subset of B. Okay, so we can say then that A is a proper subset of B. Okay, and we can denote it using this symbol. Now, suppose we have a set R with elements 0, 1, 2, 3, 4, and 5. So that is essentially equal to B, right? Because they exactly have the same elements, right? So we can say that R is equal to B, and thus is a subset of B, because any set is a subset of itself. Okay, so we can say then that R is equal to B and a subset of B, but not a proper subset of B. And we can write it using the symbolic form. We have R is a subset of B, and R is not equal to B. Okay, or just write it at this form. R is equal to B. Now, suppose we have Q. Suppose we have Q equals 4, 5, and 6. So Q is neither a subset of B nor a proper subset of B. So why is that? Because there are some elements in Q that are not in B. Okay, so we have an element 6 that are not present in B, only 4 and 5. Okay, now moving on, we can also rewrite it using in the form of quantifiers. We can say that A is a proper subset of B. Okay, going back, I'm sorry, I had a mistake in this part. So what I mean by here is that R is a subset of B, but not a proper subset of B. Okay, okay, moving on here, going back. So we have A is a proper subset of B. We can rewrite it this form. So we have for all X, if X is in A, then X is also in B. And that there exists some elements X that are in B, but that are not present in A. So you can see here, we can visualize it in this form. So understanding the first term, if X is in A, then X is also in B. So you can see that all elements of A is in B. Now for the second term, there are some elements in X such that X is in B, but are not in A. So you can see this little dot here, wherein it is an element of B, but are not in A. So an example here is that we have a set 1, 2, and then we consider it as a proper subset of 1, 2, and 3, right? So I hope you understood that. Now let us have some more examples. So 1, 2, 3, of course, is a subset of 1, 2, 3, 4, 5, a set containing these elements. And we can also consider it as a proper subset of this set. Now, is an empty set a subset of 1, 2, 3? Yes, because for all X, that for all X, if X is an empty set, implies that X is in 1, 2, 3 holds for all over empty na domain. And we already said that empty set is a subset of any set. Okay, now is empty set an element of 1, 2, 3? So in this case, what would be the answer? No, it is not an element of the set 1, 2, 3. Now, is empty set a subset of this set 1, 2, 3 with empty set? Now we can say that yes, it is a subset, and at the same time also an element of this set. All right, so let us have some more examples. Is Chebal. Okay, so let us have some more examples. Can we consider this set as a subset of itself? Yes, we have already established that any set is a subset of itself. So we can visualize it like this, a set with an element A. Now, is this set an element of this set containing two elements, A and another set? So yes, it is also an element. So we can see here that we have a big na set or a superset, and it has elements, a variable A, which is the first element, and the second element, which is a set containing another variable A. Okay, so can we consider that this set is a subset of the same set? So in this case, yes. So we can see that every element in this set is present in another na set. Okay, so we can see that this orange na set has an element A, and every element of this set is contained in the superset. Okay, so we can see that it is a subset. Now, is this set A an element of itself? In this case, no. Okay, so unless we remove the curly braces, right, so we can say that yes, it will be an element. So now, how can we count the elements of a set? So if S is finite, or meaning it is countable, then the cardinality of S may be denoted using this notation. We enclose the set into vertical navars. So the cardinality is the number of distinct elements in S. So suppose we have a set S equals 1, 2, 3. So we can say that the cardinality of the set is 3 because it has 3 distinct elements. Suppose S has one element which is a set containing 5 elements, all five threes. So the cardinality of S is equal to 1, okay, because it has only one element. Now, if S is an empty set or a null set, so what would be the cardinality of S? So the cardinality of S would be 0. We have already established that if a certain set is an empty set or a null set, it has 0 elements. Now, if S has these elements, an empty set, then another set with an empty set, then another set containing more empty sets. So what would be the cardinality of this? So we can see that we simply have to count the number of elements. So we have 1, this is the second element, and this is the third element. So the cardinality of S would be 3. Okay, so let me color it so you can see it clearly. So we have this one element, and this is another element, and this is another element. Okay. Now, if S is equal to 0 and up, as you can see, there is an ellipsis here. We can say that the cardinality of S is infinite. Now, suppose we have a set D, and assuming X is a natural number, such that X is less than or equal to 7,000. So what would be the cardinality of D? So D would be equal to, this should be 7,001. Okay, 7,001. It includes the 0. Okay? 0 to 7,000. Now, suppose D is equal to, contains all of the elements X that are in natural numbers such that X is greater than or equal to 7,000. So we can say that the cardinality of D is infinite. Now, can we possibly list down all of the subsets of a set? Yes, it is possible, and we do that by determining the power set. Okay, so the power set is also denoted or also known as P of S. And a power set or P of S is the set of all the subsets of S. Suppose we have a set S with 2 elements, 0 and 1. So what would be the possible subsets of S? So they are, first is the empty set, because an empty set is a subset of all the sets. And we could either have a set containing just one element, which could either be 0 or 1, and a subset which could contain all of the elements of S, since any set is a subset of itself. So we have the empty set, a set containing either 0 or 1, and a set containing all of the elements of S. Okay, so again, the power set of S or P of S is the set of all subsets of S. And we can write it in or enclose it in a set. So we have P of S. And since power set is a set, of course, so we enclose all this in inside the Cardinal braces. And now we also have the cardinality of the P of the power set. So if the cardinality of set is 2, since it has only 2 elements, the cardinality of the power set of its power set is 4, as we can see here. We have this one set and then another two sets containing one element, and another set containing all of the elements. Okay, so suppose we have a set T equals 0, 1, 2, and the cardinality of T is 3, right? So getting the power set of T, we have the empty set, do not forget, and we have the subsets that contain only one element. So that could either be a set containing a 0 or a 1 or a 2, and then a subset that could contain only two elements, and that could either only be 0 or 1, or 0 or 2, or 1 or 1 and 2. And another subset is itself. So we have listed down here all of the elements of T. So the cardinality of the power set of T is 8. Okay, so can we see a pattern here? Okay, so later. Note that the power set of an empty set is an empty set containing an empty set. Okay, so we note that because, why is that the case? Because in an empty set is a subset of itself. Okay, so now if the cardinality of an empty set is 0, since an empty set has 0 elements, the cardinality of a power set of an empty set is equal to 1. Okay, so now if a set has S elements, this should be S, then the power set will have 2 raised to S na elements. Okay, so we have 2 raised to S is equal to X, such that X is in S. Okay, so again, the cardinality of a power set is 2 raised to the cardinality of the set na S. So you can imagine it as each of the element having an on or off switch. On meaning it is included in the set, or off meaning it is not included in the subset. Okay, so each the possible switch configuration in A corresponds to one element in 2 raised to S. So why is it 2 raised to S? Because each na element has 2 na states, on or off. On meaning it is included in the subset, off meaning it is not included in the subset, right? So to understand it better, suppose we have a set S, and a set S has elements X, Y, and Z. Now, how do we get the power set of X, Y, and Z? So you can think of it as having an on or off na switch. So this variable X may be off, or meaning they are not included, so that is denoted in red. But if it is included in the subset, it is denoted in green, colored in green. Okay, so we have the first na subset, meaning all of the elements X, Y, Z are off, meaning the set is empty because the states of elements X, Y, and Z are all off. Now for the subset 2, we have only Z as the on, meaning Z lang yung included sa subset, X and Y are not included. Then the third subset, only Y is included in the subset. For subset, only Y and Z are included, and so on. So the possible all the possible na combinations or possible na switch configurations in A correspond to one element in 2 raised to S. So if we have 3 elements in S, this will be equivalent to 2 raised to 3, which is equivalent to 2 times 2 times 2, which is equivalent to 8 elements in the power set. Okay, now suppose we have a set S. So what would be the power set of S if S is a set containing only an element A? So the power set would be first an empty set and itself. Okay? So what would be the cardinality then? The cardinality would be 2. Okay? That would be 2 raised to 1 since we only have one element. Now, if S is equal to A and B, so what would be the power set? So the power set would be an empty set, a subset containing only one element that could either be A or B, and then a subset containing all of the elements A and B. So what would be the cardinality of the power set of this set? So we have 2 raised to 2 is equal to 4 since we have two elements A and B. Now, if S is is an empty or a null set, so what would be the power set? So it would be an empty set containing an empty set. Since since an empty set is a subset of all sets. So since this set has only one element, so we have 2 raised to 1, that would be, I'm sorry, since this set S, an empty set has 0 elements, so that would be 2 raised to 0, that will give us a 1 or 1 cardinality of 1. Now, if a set S has this element, so what would be the power set? So we have the empty set, and then containing a set containing only one element, so that would be the empty set, and then a set containing another set, and then all of the elements or itself. Okay, so since we have two elements for this also, so we also have 4 na cardinality for this power set. Now, what if the order of the elements in a set matters? So in this case, we are going to use tuples. So think of it like a Cartesian. Suppose we have this Cartesian na plane wherein we have an X and Y na planes, okay, and a point in this plane is an XY na pair of numbers to specify the location. So this refers to the X and the Y. So we have, assuming it is 2 and 3. So in a two-dimensional space, it is an XY na pair of numbers to specify a location. So what if we have three-dimensional numbers? If we have a three-dimensional numbers, 1, 2, 3 is not the same as 3 to 1 space. It is an XYZ triple of numbers. So in an n-dimensional space, it is called an n-tuple of numbers. So we have a tuple containing 2 numbers. So in a two-dimensional space, in this example, like this, we use pairs or 2 tuples. But if we have a three-dimensional space, we use triples or 3 tuples. Okay, so going back in here, why is it that, let's say we have 2, 3 is not the same as 3, 2? Okay, so this is the location of 2, 3, right? So if we have 3, 2, for sure somewhere it would be here and here. So the location is different. So that means that the order matters. So note that these tuples are ordered unlike sets. So the X na value has to come first. Okay, now our Cartesian product is the set of all ordered na 2 tuples where each part is from a given set. So we can denote a Cartesian product as A and times B, and it uses a parenthesis and not curly brackets. And for example, in a 2D Cartesian coordinates would be the set of all the ordered pairs Z times Z, or that means that possible na coordinates in a 2D space. So it could either be 2, 3, or it could be either positive x and negative y. We all have, and then we have here the negative x and the negative y, and we have here the negative x and the positive y. So that would be all the possible na coordinates in the 2D space. And we can say that it is a tuple because, as you can see, the order matters because let's say a 0.23 is different from 3,2. Okay, and the first will always denote the x, and the second will always denote the y, right? So again, the 2D na Cartesian coordinates are the set of all ordered pairs z times z, because and that z is the set of all the integers. So here's the formal definition of our Cartesian product. So suppose we have a times b, we have a pair value a and b that is enclosed in a parenthesis such that a is in a, in the set A, or A is a member of A, and B is a member of B on the other hand. So now note that again, Cartesian product is not commutative. So the order is very important. So A times B is not equal to B times A. Okay, so suppose we have a set A having values a and b, and set b having elements 0 and 1. So what will be the Cartesian product? So the Cartesian product of a times b would be a times 0, a times 1, a and 1, and then we have b 0 and b and 1. But since the order is different, b times a would be, you start from this is ordered, so b will always come first. So we have 0 and a, 0 and b, and then we have 1 and a, then 1 and b, right? So as you can see, they have different values. Oops. So another example. So all the possible grades in this class will be a Cartesian product of the set S of all the students in this class and the set G of all possible grades. Suppose we have a set S having Alice, Bob, and Chris. So that is the set of the students, and G will be A and B and C. So that those are the possible grades. So the Cartesian product will be the set of all students and the set of all possible grades. So Alice could have grade A or B or C. Bob could have grade A or B or C. And Chris could have grade A or B or C. Now, the final grades will be a subset of this. So assuming that Alice got a grade of C, or Bob got a grade of B, and Chris got a grade of A. Okay, so I hope you understood that. So what if we have the Cartesian product of G times S? So the order will be different. So we have A Alice, A Bob, A Chris. So it doesn't make any sense that there is a predetermined grades for each student. So in other words, what we did here was we selected a grade first, then select a student, which is not correct. Okay, so we can say that G times S is not equivalent to S times G. So now, how do we compute for the cardinality of the number of elements of a Cartesian product? So for sets A and B, the Cartesian product will be A times B, such that we have going back, we have the Cartesian product formally defined as a tuple or a pair of A and B such that A is in A and B is in B. So getting the Cartesian product of this will result to A1, A2, B1, and B2. So if we have finite sets A and B, so the cardinality of the Cartesian product A and B would be the cardinality of A times the cardinality of B. So in this case, the cardinality of A is 2, and the cardinality of B is also 2. So that will give us 2 times 2. And so the cardinality of this Cartesian product is 4. Okay. Now, this extends to a sub 1 times a sub 2 until a sub n. Okay. So we have tuples of, let me just make this consistent. We have a tuple of a sub 1 to a sub n, wherein a sub 1 will be in a sub 1 in set a sub 1, and a sub 2 will be in the set a sub 2 and until a sub n belonging to a sub set a sub n. Okay, so now for the set operations.